Thought. This technical analysis evaluates mechanical failures and human factors in workplace incidents, emphasizing safety engineering and disciplined conduct. A primary issue is center of gravity displacement. As the load rises, torque makes regaining balance through muscle alone impossible. For vehicle-mounted tanks, vibrations create shear forces that overcome static friction, causing sudden slips. Furthermore, failing to achieve a zero-energy state through proper lockout protocols allows invisible pressure to trigger catastrophic releases. Biologically, a 10-foot fall occurs in just 0.8 seconds, leaving no time for protective reflexes. Complacency and showboating often lead workers to ignore or exceed ergonomic limits. Ultimately, prioritizing engineering controls over brute force and staying clear of the line of fire are essential to prevent irreversible risks. Industrial rail systems present high-risk hazards primarily due to the momentum and inertia of multi-ton loads. Once a cart is in motion, its kinetic energy becomes an unstoppable force that manual strength cannot counter. Improperly balanced loads further increase the risk of derailment or sudden tipping. A critical hazard mechanism is the crush zone, where personnel become pinned between the moving cart and fixed structures like walls or pillars. This incident highlights operational failures, such as line-of-fire positioning and the lack of mechanical braking or wheel chocks. To ensure safety, facilities must maintain a 3-foot clearance rule and utilize powered tugs for heavy loads. Adhering to load limits and ensuring proper egress routes are non-negotiable for worker survival. This technical analysis evaluates structural failures and biomechanical risks, emphasizing the critical need for operational discipline. Bridge collapses caused by overloading illustrate how exceeding a fatigue threshold leads to instantaneous failure, paralyzing logistics and endangering others. Similarly, tempered glass failures highlight material stress. While surface strong, glass is vulnerable at edges where concentrated pressure triggers spontaneous shattering. Regarding human factors, carrying excessive loads like 330 lbs creates extreme spinal compression and uncontrollable kinetic energy during a fall. These incidents often stem from the efficiency fallacy, where short-term time savings lead to long-term physical or financial loss. Ultimately, prioritizing engineering controls such as safety films or forklifts and adhering to technical discipline are the only effective barriers against such preventable risks. This technical analysis examines containment failures, hydraulic instability, and human errors in industrial settings, emphasizing the need for mechanical isolation. In incidents where vehicles mount sidewalks, the absence of impact-rated bollards prevents the dissipation of kinetic energy, turning machinery into uncontrollable projectiles. Rigging errors often stem from neglecting dynamic loading, where abrupt movements multiply forces on cables. Human factors, such as entering the line of fire or instinctively trying to stabilize shifting loads, lead to entrapment in pinch points. Furthermore, sudden hydraulic pressure loss or brake fatigue can cause platforms to free fall or vehicles to drift. To mitigate these risks, establishing exclusion zones, utilizing mechanical wheel chocks or safety struts, and employing spotters for 360-degree inspections are vital. Ultimately, prioritizing human life over property and respecting physical laws remain the core principles of safety. The technical analysis of rotating equipment highlights the extreme dangers of in-running nip points and mechanical entanglement. Industrial rollers create frictional forces that far exceed human strength, dragging personnel into hazard zones almost instantaneously. Because the window for entanglement is measured in milliseconds, it outpaces human neurological reflexes, making self-extraction nearly impossible. Personal attire, such as loose clothing or long hair, acts as a conduit for this force, while gloves can inadvertently increase snagging risks. This incident reveals critical deficiencies in engineering controls, specifically inadequate machine guarding and the absence of functional emergency stops. To ensure safety, operators must strictly follow lockout protocols and maintain a safe distance from live equipment. Ultimately, combining robust mechanical safeguards with disciplined awareness is the only effective defense against the unforgiving nature of industrial machinery. This technical analysis examines the structural and operational factors in a heavy vehicle loss of control incident on a bridge, emphasizing the critical link between infrastructure and vehicle safety. The incident began with a loss of directional stability, likely due to mechanical failure or operator lapse, which allowed the vehicle's massive kinetic energy to overwhelm the protective barriers. The critical impact angle focused force on specific structural points, breaching the perimeter and transitioning horizontal momentum into a vertical free fall. This highlights that existing railings may lack the load capacity for heavy vehicles, necessitating upgrades to high containment systems like jersey barriers. Furthermore, rigorous preventative maintenance of steering and braking systems, combined with strict operator discipline, is essential. Ultimately, reinforcing roadside infrastructure and ensuring emergency preparedness are indispensable pillars for protecting public transit passengers. This technical analysis evaluates the physics of motion, energy release, and human behavioral risks in industrial settings, providing essential safety benchmarks for labor operations. A critical issue is center of gravity displacement. When carrying high stacked loads or standing on convex surfaces, stability decreases sharply, making balance impossible to maintain against sudden torque. Furthermore, low-friction metal surfaces allow inertia to accelerate a sliding body faster than human reflexes can respond, resulting in high-impact falls. Hazards also include stored energy, where invisible pressure in glass or machinery leads to catastrophic failures when elastic limits are exceeded. Human factors, specifically entering the line of fire or falling into the experience trap of overconfidence, remain primary catalysts for incidents. To mitigate these risks, organizations must establish exclusion zones, prioritize mechanization over brute force, and enforce 360-degree inspections. Ultimately, technical discipline is the final barrier against preventable risk. This technical analysis examines the critical mechanical failures and high-pressure hazards in heavy vehicle tire maintenance, emphasizing the necessity of safety compliance. Engineering failures often involve pneumatic energy release, where tire pressures up to 120 psi create high-velocity shockwaves or launch multi-piece rim components as projectiles. Positioning is equally critical. Standing near the sidewall places workers in the line of fire, while servicing tires on metal beds can intensify shockwaves via reflective surfaces. To mitigate material fatigue and calibration errors, technicians must implement engineering controls like safety inflation cages and clip-on chucks to maintain a safe distance. Furthermore, a strict no-shortcuts culture and three-point inspections are vital for identifying pre-failure indicators. Ultimately, combining proper equipment with rigorous situational awareness serves as the final defense against the immense power of compressed air. This technical analysis examines the critical mechanical failures and operational risks associated with high-pressure systems and infrastructure integrity. Rapid thermal expansion during hot work on unpurged vessels can turn containers into improvised explosives, while high-pressure tire failures release shockwaves capable of significant internal trauma. To mitigate these risks, maintaining a safe distance from the line of fire and avoiding pinch points between moving vehicles and stationary structures is essential. Furthermore, structural failures in barriers highlight the need for high containment systems like jersey barriers to manage kinetic energy. Effective prevention requires strict adherence to lockout, tagout, lockout protocols, the use of mechanical safety struts as secondary fail-safes, and the enforcement of exclusion zones monitored by independent spotters. This technical analysis examines structural failures and kinetic energy dynamics in industrial collisions, emphasizing the need for spatial awareness and mechanical isolation. When a forklift impacts a crane, its massive weight generates extreme momentum, a K-frac 1-2, creating lateral forces that cranes are not engineered to withstand. This displacement of internal stress triggers catastrophic failures in booms or counterweights. Furthermore, equipment drift on inclines proves the failure to neutralize potential energy PMA, highlighting why mechanical wheel chocks are mandatory fail-safes. Human factors, such as operator blind spots and the absence of a signalman, often lead to intersecting trajectories in blind zones. To prevent such disasters, facilities must enforce exclusion zones, strict stop-check-go protocols, and rigorous maintenance. Ultimately, size does not guarantee safety. Only disciplined coordination can protect robust structures from the laws of physics.